Yes, yes, yes.
Okay.
I will hide share option. Okay. Somebody started recording.
Yeah. This is my circuit,
Okay.
and I had to find the transfer function,
Yes.
and to do this, I separate the circuit in three parts.
That's very good idea.
And this is just a simple inverter, here an
Yes.
integer,
Yes.
and here a low pass filter.
Okay. But with two inputs.
Yes, and
Yes.
this is on this part that I have a question.
Okay.
I have the function transfer UIZ
This is
over
IZ is output. UL is input.
yes.
Okay. IZ means islas, which is out.
Yes, islas and ulas.
ULAS is input.
Yeah.
Okay.
And I found something like minus R3 on R. Oh, sorry.
This on the input is very well known lossy integrator with summer
Yes.
summator together with two inputs, we say.
Yes,
The
and
summation.
S R3 C. And I have a question with R2.
Okay. Where it comes?
Oh, yes, I don't know if I just had to put it there or if I had to include there too.
No, no, no. You just you write another expression.
Yeah.
Let's say call this one, which you already wrote, U is over UL1.
Okay.
This is over UL1. You put 1 by L. Okay, that's good. And then you write another same expression and you replace only R1 by R2. You write U is over UL2. And you write everything the same except R1.
Except
Just
R1.
yes, yes. R1 replaced by R2. So okay, that's good. And everything else is the same.
Okay, and I just have to times the two equation.
Now you have to add the results of two equations, which are correct. What you have to do is from the first, you can write U is 1.
Yes.
From the second, you can write U is 2.
Yes.
And then U is the summation of U is 1 plus U is 2.
Okay. Thank
Do
you.
you see? This is
Yeah,
very
yeah, yeah.
simple.
Okay.
This is the most simple way to do it.
Okay.
This is superposition. Okay, that's it.
Yes. Thank you very much.
Plus U is 2.
Yeah. I,
Okay.
thank you very much.
Okay, everybody, because we have already started, it is good that we continue with our lectures today. So our lecture will today continue where we stopped last time. And this will be inverse Chebyshev approximation. Indeed, we will today continue with chapter number 8, which is inverse Chebyshev and Kauer filters. So this is continuation from the last time where we said a few words about Butterworth and Chebyshev filters. So these filters are somehow grouped together because it is logical, and you will see why. So today we continue with inverse Chebyshev approximation. We will of course not do it all in big detail. We'll just say the most important facts about this, and then you will, if you have enough time and if you have enough will, you will learn it from the book, which you have, of course, in PDF, which I showed you. Okay, let's start with inverse Chebyshev filter, and we'll also translate this what is written here in English. Inverse Chebyshev approximation. Okay. So this can be derived into 3 steps. I will not look into very big details, but just that you have a feeling. This is also what you can see in the book, but I think it's good that we do it step by commenting. So it can be derived in 3 steps. Step 1. Start from low pass Chebyshev, or we call it Chebyshev1, Chebyshev normal characteristic. It looks like this. It's not something what we don't know. Here is a ripple. And here in the, this is stop band, this is pass band, pass band, stop band. Okay. And then we recognize this value as 1 plus epsilon square. The characteristics is like this. One plus epsilon square Tn square of omega. This part here, everybody knows, is characteristic equation. This we remember from the last time. Characteristic function, not equation. Characteristic function. This is, of course, Chebyshev, and it is here. So we know this already, and then we continue to the second step. Step number 2. Subtract it from 1. Then we have 1 minus H Chebi. And then we obtain, you can try it, it's very simple. Something like this. And it is interesting to plot it. What you get is something like this. Here is unity. Here is unity. Here is unity. So we have gain from 0 to 1. We don't have decibels here. And then what we get here is, of course, epsilon square over 1 plus epsilon square. And it goes to unity. So this is this function. And then in the step 3, invert frequency axis. Omega goes to 1 over omega. We will have the next thing. So it goes something like this. Here is 1. Here is still epsilon square over 1 plus epsilon square. Here is 1, 0. And the characteristics looks like this. This is called HIC. IC means inverse Chebi, or somebody call it Chebi type 2 of J omega. Of course, everything is squared, and it looks like this. Epsilon square, T in Tn square, 1 over omega, 1 plus epsilon square, Tn square, 1 over omega. So this is called inverse Chebyshev characteristics. And as you see, it's simple, and it starts from simple Chebyshev number 1 of normal Chebyshev, and always you can derive it from it. But why do we learn it separately? This is because this characteristics has some properties which are, for example, you see it has, I'm writing red, it has zeros which are lower than infinity. So these zeros lower than infinity, they make problems if you want to realize them, if you don't use a proper circuitry. So this is one thing. Butterworth and normal Chebyshev, they don't have such a zeros. They have all the zeros in infinity or in the zero. But these here are zeros lower than infinity. Of course, how we find this value here? We know that this Tn, this is Chebyshev polynomial. It has a value, for example, of omega. If we put omega equal to 1, it has value 1. So you have this point here. So this is both for odd and even order. For both odd and even n. Okay? So this is small inquiry. We continue with the characteristics of our inverse Chebyshev. It has the same order. So I write here. Same order as Chebyshev 1. But it has lower pole Q factors. And because of this, it's it has more flat group delay, or with, let's say, it has a group delay with less variations, lower variation. So low variation group delay, or in other words, more linear phase. And because of this, it's appropriate for video applications. Or for data and data transmission. So everywhere where you need linear phase, you will rather use inverse Chebyshev approximation than the normal Chebyshev approximation. And of course, it has here maximally flat. And here you have equi-ripple. So this is characteristic of inverse Chebyshev approximation. It is derived very simply from the normal Chebyshev, and it's applicable to some applications where it is needed to have some linear phase. Of course, you can learn everything in the chapter 8 about it. So let me see. This process of derivation is here. So you see it's very simple. You can learn it from here also, but we wanted to demonstrate it, how it looks like. Then here is another equation which is useful for calculation of the inverse Chebyshev in decibels. Here is plot of inverse Chebyshev in decibels. This here is loss. What does it mean, loss? This is negative decibels. If you multiply decibels by -1, you will have loss. You will not have gain. So this is equal to minus gain, of course, when everything is in decibels. Okay. Now we will here not write about on our right side about this anymore, but I just want to show you this is the equation for the order of the Chebyshev approximation. Okay? Or inverse Chebyshev, this is the same order. Now we continue with Cower. So this was enough. You see here inverse Chebyshev on our creation slides. So this is something what we now finished. Now we continue with Cower approximation. So how is Cower approximation defined. We go here down. Cover. It's sometimes called Cover-Chebyshev. It's also called elliptic, or somebody only says cover. So, but everything this here is correct. Application. So what is now important to say about this? We said here before that in the transfer function, I will show it here. In the transfer function, we recognize something what is called characteristic function. So look at this. Okay. Now we try to cover Chebyshev. Sometimes is used CC of J omega as 1 over 1 plus epsilon square Rn square of omega. And this is our new K or characteristics function. Here is something new, Rn, what is called a rational function. Rational function, recall that at Chebyshev, there was Tn of omega, which is polynomial. So the two most important words here are polynomial and a rational function. Okay, so what is the difference between rational function and polynomial? Polynomial was before at Chebyshev. Rational function looks like this. Okay. We'll very quickly know why. N even, and we have another form for n odd. For n odd, cutoff of the, let's say, cutoff frequency of the passband is omega p equal to unity. This is always normalized to unity. Then we have cutoff frequency of the stop band. We will call it omega s. That's this one here. Okay. And then we also recognize omega r, which is omega s over omega z. This is reflection zeros. Why reflection? That's something what we'll see later. Omega z transfer function zeros. They are both symmetrical around square root of omega s. Of course, omega r times omega z is equal to omega s. So this is small truth. Okay, now we can continue. We will use some more space. Okay. Here we can write we could do it better. We must press this one. Like this. Here we can write or plot, let's say better, how it looks like. I mean characteristic function. This value here is our epsilon. This is some other value which we'll call delta. This is k of j omega square. Let's say our characteristic function, which is a rational function. This is here. Okay, now we'll try to plot it. Something like this. This is forbidden area, like some specifications. Okay, here we call this and this and this reflection zeros. Omega R1, omega R2, omega R3. And then we will call these here omega z1, omega z2, and omega z3. Here was unity gain, unity frequency. This is omega p, which is normalized, and it is equal to 1. This is omega s here. Here in the geometrical middle is square root of omega s, and then we can see that these are symmetrical. For example, this one is symmetrical with that one over this omega s. So this is something what is very simple to see. Okay, because this elliptic function has such a special characteristic function. It has the amplitude frequency characteristic which looks like this. Because we must use this equation here, of course, with this k and epsilon and Rn, then we can plot that it looks like this. This is here 0 dB. This is absolute transfer function. This is unity. This is omega s. Let's say like this. This is A, B, A, S, or we'll call it later. Here we have some ripple. The same like by characteristic function. And we have on the place of these zeros like this. Okay, this is 20 log, and this is in decibels. If it is plot like this, if the gain is from 0 to 1, then it will be very easy for us to show how it looks like. I will very quickly plot this also. So in the sense of gain from 0 to 1, it looks like this. So here are zeros. Let's call it omega z 1, omega z2. So when the gain is 0, if you make a logarithm of 0, you have minus infinity. That's why those here goes to minus infinity. I think you understand it. And then this guy here is epsilon. This is delta, or something like this. And here is without 20 logarithm. Here is 1, here is omega s. And then we can call AP as maximum pass band ripple. We can call AS, somebody use a max. Then here somebody use a min. So we could write here a max and a min. Minimum stop band attenuation. Okay. Then we see this here, these maximums here, like here, they are all the same. So we call this equi minimum characteristics here. Here it's equiripple and so on. There are many names for this kind of characteristics. But what is important for us to see how many parameters we have in elliptic approximation or CC or Cauer-Chebyshev. We have four parameters. These are, so we have 4 parameters. These are A max, A min. The next one, which is very important, is omega S. It's transient region width. This is this guy here or here. So this is, and then or a cutoff stop band. And the fourth parameter, probably you can now see which one. N. This is order. This is parameter number 4. So we have 4 important parameters. Okay. We use 3 parameters and calculate 4. And that the 4th is the best. This is design procedure. Oh, I write it here. Design. We choose 3 parameters and calculate 4th, which is then optimal. So the 4th, which is then calculated, is optimum. So let's say we choose A max, we choose A min, and we set the width of the transient region or the minimum or the cutoff stop band. And then what we calculate is n, which order filter we need. So this is all what we have to say for now about this kind of elliptic filters. But here we want to use this part of our canvas to plot all four filters which we have learned so far. For example, we had Butterworth, like this. We have another one. Okay. This is from last lecture. So Butterworth has maximally flat characteristic in both bandpass and stop band. So here is maximum flat, maximum flat. What about Chebyshev? He has equiripple in the pass band and maximum flat in the stop band. And then today we continued with Chebyshev 2, or inverse Chebyshev, which is like this. Here is maximum flat, maximum flatness. Here is equiripple. And finally, we have this guy here at the bottom, which will plot here again. Like this. We have this. We will plot it better. This is elliptic, or CC, which means Kauer-Chebyshev. Okay, and then we have equiripple here, equiripple here. We have here pass band, pass band, pass band. Here we have stop band. Here we have transient band or transition band in between pass band and stop band. Okay, so we said that for the price of some ripple in the passband, we obtained something. Let's say, example, we have to design a low pass prototype filter satisfying some specification like this. So we must satisfy this. And then this is given omega p, omega s. This is unity, or it can be 0 decibels or whatever. A max, A mean, and so on. So let's say it is given, and we will calculate the order of each of these filters. For Butterworth, we have, for example, something like 21. And then we see, oh, it's very big order, it's very complicated filter. And then for the Chebyshev, we calculate the order n is equal to 15. Okay, that means we have saved a lot of parts of the filter. Then we try to calculate inverse Chebyshev filter, and then we see it has the same order as Chebyshev filter. This is 15 also. Okay, that's very good. But the order is the same. We have maximum flatness in the passband, we have some ripple in the stopband, and because of giving some ripple anywhere in passband or in the stopband, we have reduced the order from 21 to 15, which is okay, it's very good. But now we decided to put a ripple both in the passband and in the stopband, and we have to calculate it somehow, and people found that it is very efficient if you use elliptic integrals to calculate it, and then they said, aha, then this filter is very, very efficient, and we obtained the order of this filter, for example, n is equal to 7. So this was one live example. We will not calculate it in details because we don't have so much time. But when we start from specifications or specs, then we try to design Butterworth or Chebyshev or inverse Chebyshev or elliptic filter, and we obtain different orders. So what is good for us, we see that Chebyshev and inverse Chebyshev have the same order, which is lower than Butterworth, but elliptic filter is the best. He has the lowest order. And now we can group these two filters, two pair of filters, into two very important groups. First group and second group. What is the first group and what is the second group? The first group is like this. It's called all-pole filters. When you open any book, you will find this. What is meaning the all-pole filters? All-pole filters says that it has zeros somewhere in 0 or in infinity, but it doesn't have zeros that are lower than infinity. So zeros are in 0 and infinity only. So that means these are the most simple filters, Butterworth and Chebyshev, and we don't have some circuitry to realize zeros. Finite zeros filters. Zeros exist between 0 and infinity. Zeros exist there. Okay, we can see them. Here are the zeros. This is 0, 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 this is 0. But of course, we have here 0 in infinity. We have also here some 0 in infinity, maybe. And here we have only zeros in infinity, but here we have 0 in infinity, but also we have these finite zeros because it is 0 here. So this is the basic difference why we learn separately in these two chapters. So this is chapter 8. You see everything about, just a moment, let me see. So last time we learned chapter 6 and 7, and this time we learn chapter 8 together, inverse Chebyshev and cover filters. So they are grouped like this logic. Okay, so today we have finished the lecture about inverse Chebyshev and cover approximation. So this is cover in the passband, and it was here the whole cover together with passband and the stop band. Okay, now we will make a short pause, and we will after. So just before pause, I will show you what you have to learn today. Chapter 8. Here is everything about inverse Chebyshev. This is what we have seen already, and then you can continue with cover. Here is cover 8.3. How you develop it. Here are pole and zero placement of cover. This is what we didn't write here today, but you have to look at this in book. And then this is our rational function. And then you at the end you can find how can be performed the design of cover filter. This. And then at the end you have tables. Finally you have tables. And this is example how to calculate it. So this is what you have to do it by yourself if you want to learn how to design all these 4 filters. So you have it in the book. Here is another table of cover filters. You see it's not so simple. There are many numbers which you don't need to calculate. You just have to read from the table, but you have to recognize them. Here is another. Here is second order elliptic. This is third order. And you have fourth order elliptic function. And of course, Here you have one example, which is solved here later, example 8.4, and then you can try to design such a filter. This is typical body characteristic of the elliptic filter. And as you see, it's very steep here. Okay. Here is comparison of all these filters. This is what I will not show you now, but we will continue after our short pauses with frequency transformations. Okay, that's for the first hour.
Okay.
Okay.
So everything is recorded. It will not be problem. We'll make 10 minutes or 15 pause.
Okay, perfect.
So we continue with our lectures. So we will start new. Okay. Here we will have 2000. And we'll okay. Okay. Next is about frequency transformations, and we'll say for a few words for the introduction. So later you will be able to read the book, but before you listen to this lecture, so this is more efficient. This what I will derive to you now is from some other book, so it's not from this book here, but it is more easy than for you to understand what we are talking about. Okay, so we will say a few words about frequency, transformation. As you see, we always start in our lecture with low pass, for example, like this. And we call it low pass prototype. It's some kind of function. So low pass prototype. We know h of s. We know. The question is what we can do in a simple way to obtain, for example, bandpass like this. So we want to have from this one the bandpass which we want as a result. So now this is a question, how to do it. We know this. And what we can do in a simple way to obtain h bandpass of s. So this is what we want to research today. And of course, we can recognize that here, this is passband. And here, this is passband. here is stop band. Here, this is stop band. Okay, so something what we expect is that there is some transformation of the frequency axis, which will connect passband with passband, and also stop band with stop band. Znači SB. This is here PB, passband. So how we can, for example, connect stop band to stop band and passband to passband and obtain such a transformation. Of course, what we didn't write in our case of low pass prototype, we know that this can be written like this. So our characteristics is symmetric from the mathematic point of view, and then this all here to negative omega is also passband. Okay, but this is something what we just extend for mathematical purposes. Okay, now we will have the following designations for omegas. This one here, we will put this bar, and this one here, we can divide by omega 0 and designate by normalized omega. What does it mean? If you have something like this, here is probably 1000 or 100, here is 0. Then if you divide by omega 0, which is equal to 100, you put this here, you will have the following axis by large omega, and here it will be 1. So we can normalize if we divide all values of omega axis by some omega 0, and then we can replace it by capital omega, and this is called frequency axis normalization by omega 0. So this is something what is not new to us. Okay, now we can plot the following picture. Here in this picture is this omega bar. This is low pass prototype axis. You will see at the end that this is very, very useful to analyze. And this is normalized, of course. This is as if we divide by some omega 0. And then you can plot this here. The green area as passband. This green. Okay. This goes from -1 to 1. And then we can here plot on this place, we can plot a normalized frequency axis of the band pass filter. So band pass BP axis of course, omega is something like omega over omega 0. It's also normalized. Okay. And then we have something what we want, like this here. We call it omega L and omega high. And this will be our new passband area. So what we need the following connection. We need that this point here makes picture in this point here. So for point omega equal to omega L, we connect omega bar equal to -1. For point omega equal to omega h, omega high, we connect omega bar to +1. Okay, and then we can see what kind of function we need. We can guess that there must be a function like this. Oh, no, just a moment. It cuts on this place. We call this place omega 0. We will see what is the meaning of omega 0 small. We will find the meaning. Okay. This function can be designed using another function, which is called omega, and another, which is called -1 over omega. So this function here is nothing else but omega -1 over omega. And of course, if we want to have these 2 points satisfied, then probably we'll have to put some k, which is something what is constant, what is free, because if you move this here and you move this here, you have probably different value of k what is needed. So we must include some k. Okay. Good. Now we will also call something what is always known as bandwidth. It's this here, B, bandwidth, or let's say normalized bandwidth. We will call it Bn. This is omega h minus omega L. Of course, if we multiply everything by omega 0, then we have B, which is Pn time omega 0, which is omega 0 omega h minus omega 0 omega L, which is small omega h minus omega L. These are denormalized. Okay, so we can use either this notation, which is normalized, it's divided by omega 0. It's not a problem. Or we can then back multiply it by omega 0, and we can use another notation, which is denormalized. It is B equal omega H minus omega L. So this is also useful to say now. This is denormalized. Okay. Now we can pull it down. Good. So for now we have the basic equation, which is equal to f of omega, and this is equal to k times omega minus. So our frequency transformation must look like this, or we can write k like omega square minus 1 over omega. Okay. Now we must find what is k. Good. For the first point, we call it point A. That's this here. We can write this equation like minus 1, because it's minus 1 here. Minus 1 is equal to k to omega L, that's this one, square minus 1 over omega L. For point B, this is another one here or here. We can write that plus 1 is equal to k times omega h square minus 1 over omega h. And now, after some calculation, we can calculate it here quickly. Minus omega L over k is equal to omega L square minus 1, omega L square plus 1 over k, omega L minus 1 is 0, omega L 1, 2 is minus 1 over 2k plus minus 1 over 4k square plus 1. Here we can write that omega h square minus 1 over k, omega h minus 1 is equal to 0, omega h 1, 2 is equal to plus 1 over 2k. Here is plus minus 1 over 4k square plus 1. Okay, now we have solution for these two, and we can continue. What is B? Bn is omega h minus omega L, and this is very simple. If you introduce these two here, then what will be subtracted is this. And what is left is 1 over 2k minus 1 over 2k is 1 over k. In the next step, if you try to multiply omega L times omega h, very fast you will see, if you multiply this and this, that this is equal to like this, a plus b times a minus b is equal to a squared minus b squared. This is a, this is b, and so on. You will have plus minus square root 1 over 4k square minus plus 1 square minus 1 over 2k, and this is equal. This is equal to 1 over 4k square plus 1 minus 1 over 2k square. This is reduced. This is equal to 1. So we have another two very important equations. One is Bn is equal to 1 over k, and another one is omega, and this is of course omega h minus omega L, and omega h times omega L is equal to 1. So this is what we have derived so far. Now we can continue. We look at this, our equation. We write it again. Omega is equal to, so k we now know from here. This is 1 over Bn times omega square minus 1 over omega. So this is from the first important equation. From the second important equation, we see, because we know that omega h is omega h over omega 0. This was omega h times omega L over omega 0. This is omega L. This is equal to 1. And then we have that omega h times omega L denormalized omega 0 square. So these are two very important expressions. Of course, you always remember that this is normalized. Okay, now omega 0 is geometrical mean of omega h and omega L. Okay. And also we remember that Bn is normalized bandwidth, which is B over omega 0. Okay. Now we can continue. We can continue. We use substitutions. S equal to J omega for frequency characteristics. Of course, we can also use S bar is J omega bar, S is J omega, and so on. And then we will write here our equation again. So omega bar, this one from below, omega this one, 1 over Bn, omega square minus 1 over omega. So this can be using this knowledge here and using the knowledge that omega is omega over omega 0, and again Bn is B over omega 0. Using all of this, here we can continue. Omega bar is omega 0 over bandwidth times omega over omega 0 square over omega 0, and this is equal to omega square over omega 0 minus omega 0 over B omega over omega 0, and this is omega square minus omega 0 square B times omega. Okay, and then we go with these substitutions. We can include indeed omega like S bar over J, and this omega without bar like S over J. So we have S bar over J is equal to omega square is S over J square plus omega 0 square over B times S over J. And after some calculations, you know this, if J is in denominator, it goes to minus J into nominator. Minus J times S is equal to minus S square minus omega 0 square over B S times J. Now J's are being deleted, and this minuses becomes plus, and at the end of our work we obtained this expression S square plus omega 0 square over Bs. Now you see, and this is called low pass to band pass transformation. Now you see, we started from this picture here, and we obtained, after long calculation, we obtained this expression. So look, it's not quite simple. You see in the book this equation, and you don't, this is called low pass to band pass transformation, and you don't know how it is derived. Now we have derived it. And we will find the meaning of omega 0. Of course, omega 0 is here. This is omega 0 over omega 0 if it is normalized. But then it is unity here. But the meaning of omega 0, this is center frequency. This is center frequency. This is omega 0. So in the beginning, we divided the axis of our goal function, and then we have found that this is omega 0, the center frequency, this number omega 0. Okay, what this transformation gives, of course, here is bar, because this is low pass prototype. This here is normalized still. This here is not normalized, it's denormalized. So we say by transformation, we beside immediately do the denormalization. And what we get is from normalized low pass prototype, we obtain geometrically symmetrical bandpass. Just a moment. Filter. So you see how it is derived. Now I will show it on one small example. How it works. Here is low pass. Low pass prototype. This is omega. It's normalized to unity. This is characteristic. For example, the characteristics have some shape like this. It can be whatever. But let's say it's second order. It's not second order. It's, for example, let me make second order. This is second order. Okay. How it works? It works like this. Okay, this is normalized. This is omega. This is not normalized, but doesn't matter now. This is omega 0. This is central frequency. This is omega L, omega H. This here is called bandwidth. And then, of course, omega 0 is square root of omega H times omega L. This is geometrical mean. And the characteristics looks like this. It has the same shape as this one here, and now it's fourth order. It has all these points the same. How we obtained it? We obtained it by S, S square plus omega 0 square over B times S. So we apply this low pass to high pass transformation, and we obtain from low pass prototype band pass filter with bandwidth B and central frequency omega 0, and which is of course denormalized because we can put here omega 0 and B whatever we want. Now at the end I would just like to say what is K? K is equal to omega 0 over B, which is equal to omega 0 over omega H minus omega L, or which is equal to 1 over omega H if we use normalized omegas. or this is 1 over Bn. And then finally, it's usually given special name, which is called Q. This is called Q is called quality factor. Now you remember that we have used last time quality factor in connection with bandwidth. So we said, aha, those filters who have too small quality factor, they cannot obtain narrow bandwidths. So this was to remember from the last time. Of course, if we draw these characteristics as 20 log absolute h of j omega, like this. If you have, for example, or what you have here, just a moment. So if you have decibels, if you have dB, then this roll-off is for if it is second order, then you have it as 40 dB over decade. In the stop band, of course, at high frequencies. So here, then you will have, if you make it in dB, you will also have, so this is minus 40, you will have minus 40 dB over decade here, and you will have plus 40 dB over decade here, if in dB, or let's say in decibel. Okay, of course, second order transformed to fourth order, but the roll-off, which was 40 dB, turned into two roll-offs of 40 dB. So now it will be 80 dB, but it's from both sides 40. So this is the reason why. So this derivation was, let's say, quite long, and probably maybe too long for our lectures, but it's good to see it. And then you can all find it in our book, which we use for our lectures. So here you have low pass to band pass transformation. I just want to say that low pass to band stop is very similar. It's like this. It can be derived in the same way. This is low pass to band stop. This is our. There is also low pass to high pass, like omega cutoff over S, and so on. Low pass to low pass. This is normalized to S over omega C. That's denormalization only. So there is also possibility to write for all four cases. Okay. So this was our lecture about frequency transformations. Okay. Next lecture will be about realization of passive electrical filters. And this is something what we will do after New Year. So for now, I think you have enough material to learn. And we will continue on the Thursday after New Year. I will put you a call for the lecture. So you will find it. And then we will see us in the new year. So for now, I wish you everything good in the new year and that you have fun with learning analog electrical filters. That's
Thank you.
all. That's
Thank
all
you.
for now. Have a good day. Have a good end of the year.
You too.
Everything the best for the seasons greetings. Okay.
Yeah.
Okay. Thank you.
See you
Good
after
day.
New Year and have a good time.
Me too.
Okay. Bye bye.